I will present on the coating of cathode active material to improve the stability of the interface between cathode active material and the sulfide electrolyte in sulfide-based or solid-state batteries. A liquid electrolyte currently used in lithium-ion batteries has the advantage of high ion conductivity and excellent contact formation with electrode materials, but it is a combustible organic material with low thermal stability, so it poses safety issues such as fire and explosion. To solve the stability problem of lithium-ion batteries, we are developing solid-state batteries that replace liquid electrolytes with solid electrolytes. A solid electrolyte has high thermal stability and no risk of evaporation due to an increase in operating temperature or leakage due to an external impact, so it has a wider electrochemical stability window than a liquid electrolyte, and a potential cathode material or lithium metal can be used as a cathode. In addition, there are no need for external packing for separation or explosion, so direct stacking between cells is possible. However, solid electrolytes have lower ion conductivity than liquid electrolytes and are difficult to form contact with electrode materials, so the contact interface resistance is high. As a suitable material, sulfide-based solid electrolytes are being actively studied. A sulfide solid electrolyte has high ion conductivity like a liquid electrolyte, and its ductile mechanical property provides excellent contact between electrode materials. The problem is that it reacts with moisture in the atmosphere to produce toxic hydrogen sulfide, so care must be taken not to be exposed to the atmosphere during manufacture, and oxidation reactions occur at the interface with the cathode active material. I'd like to do some research to solve this second problem. The oxidation reaction at the interface between the cathode active material and the sulfide electrolyte occurring in the sulfide or solid-state batteries causes interfacial resistance, capacity fading, and a decrease in long-term life. This can be solved by coating a cathode active material with a stable metal oxide such as lithium niobate to prevent direct physical contact. Therefore, it is necessary to develop coating materials and economical and efficient coating processes with excellent lithium-ion conductivity while effectively reducing interface resistance. As for research trends, materials such as LNO, LTO, LGO, and alumina are mainly used as coating materials, and wet chemical is traditionally the most widely used coating method, and dry process, PLD, and ALD are also actively used recently. It shows a general experimental method of the Jorgel process among wet chemicals, which is the most studied method. First, dissolve the precursor of the coating material in the solvent, and then add a cathode active material to the solution and stir it and at room temperature. Then blow away the solvent and sinter at 500 degrees under the flow of oxygen to create a coated cathode active material. This process is to coat the cathode material with a coating precursor first, and then synthesize it during the sintering process so that the desired coating material is finally coated on the cathode material. Wet chemical enables uniform coating, and the Jorgel process I just introduced has the advantage of being the worst and the simplest coating method. However, this solution and drying steps are required, which are time-consuming and quite difficult to control the thickness. Spray coating can shorten the time, but it requires expensive equipment. In addition, all wet chemical coating have environmental problems due to organic solvents, so it can be solved to introduce a dry method that enables uniform coating without using a solvent. The figure below is observed with SEM after coating with a wet chemical method and dry process. It can be seen that the surface of wet chemical is smooth when viewed at a low magnification, but the surface of dry coating is not smooth as if it is not uniformly coated. The cathode active material by the dry process has a relatively simple experimental process. Put the cathode active material and the material to be coated in a dry coating machine. Mix the coating material particle size at a low RPM of about 1 minute and then mix the coating material at a high RPM of about 6 minutes to adhere better, and dry it in a vacuum oven to remove moisture. Comparing the electrochemical characteristics of the coated cathode active material and pristine, it can be verified that the overall capacity fading is low. The characteristics at a high rate are improved, and the long-term life is also improved. In addition, the resistance was also very reduced, and it can be seen that the interfacial resistance by the oxidation reaction was effectively suppressed. The ideal coating material should have flexible properties such as cracking on the surface of cathode material due to volume change during charging and discharging. In terms of mechanical properties, electrochemical properties should not exhibit redox activity within the potential range of cathode. It should also have low mobility from ions other than lithium ions. Materials such as LNO, LTO, and LGO with suitable properties are currently the most widely used cathode coating materials. They are relatively stiff and brittle, but they have a slight change in volume during charging and discharging, low electron conductivity, and reasonable ion conductivity. When NCM and NCA were used as cathode active materials in dry processes, materials such as LNO, LTO, LGO, alumina were mainly used. Based on this, LNO, which is well-known so far, will be tested first, followed by LTO and new suitable coating materials. NCM811 will be used as a cathode active material, and the results of dry coating will be studied to be as similar to wet as possible by comparing wet and dry, making it uniform and excellent coating effect. That's all for the presentation. Thank you.